afternoon to all the people who have registered so far. Welcome to this webinar, ESA webinar on design for the Demise. My name is Rita Nacenti, and I would like to make some kind of administrative consideration or logistical consideration. First of all, we have reached the capacity of WebEx, so we will most likely be at the peak about 250 people. Because of this, I would like to ask everybody to switch off the camera, only the presenter, or in case when the person will ask a question, should have the camera on. This is to limit the data rate and not to create problem with that. Second point, everybody should be muted because sometimes there are background noises, and anyway, the host will mute everybody. So even if you don't mute, you will be automatically muted by the host. Another point which is, I think, important to tell you is that we will record the webinar. Some people could not join the webinar and they have asked us to record it so that we can distribute the recording afterwards. Of course, afterwards, we will also distribute the presentation that we are using. So you will receive it a posteriori. The webinar is split in a way into two parts. The first part is more generic, and we will finish it up with a question and answer, and then we will go to a more detailed and presentation, which is maybe a bit more targeted for experts. Of course, welcome to stay with us until the end. Please, during the webinar, do not hesitate to use the chat to ask questions or make comments. They will be monitored by the moderator. With this, I would propose that we really start and we move to the next slide. So, the speakers today are going to be myself, Nacenti. I am the head of the CleanSpace office. Antonio Chiazzo, who is a system engineer at ESTEC, and Tiago Soares, who is another system engineer and who is responsible for all the action related to the end of life of the satellite and upper stage. We also have moderators who will be chatting with you and taking care and noting your questions, and these are Salo Morales and Andrew Wolan, two system engineers in the concurrent design facility, and Stein Lemon, who is a senior state degree officer, who I think is with us at the moment and will try to join us as soon as we finish the other meeting. We are all quite busy with other activities. Okay, if we can move to the next slide. So the agenda is to give you a very about the rationale for Demise, the assessment, the techniques. Then we will start with the question and answer, and then we will go moving to the Demise verification and the vision, and then again another session of question and answer. Our plan is to be over in around 1 hour. Next slide. So the rationale, I can go directly to the next slide. So I think that most of you are aware, or all of you are aware, that we do find cases of upper stages of rockets or satellites on ground. They fall down because they do not completely disintegrate while crossing the atmosphere. Most of the pieces that we can recognize are actually tanks, because those are evident objects. But we do believe that there are other objects which have fallen down, but they have not simply been recognized as being space hardware. Go to the next slide. So You're going to be too far. Yes. So let's talk very, very quickly about space debris. As we have polluted the Earth, we have polluted the space, and we have polluted particularly two zones which have been defined as protected zones. This is the low Earth orbit, up to 2,000 kilometers, and the geostationary orbit. By now, guidelines, regulation on what you have to do at the end of life in order not to create debris. And one of these guidelines says that you need to remove your satellite or upper stage at the end of life within 25 years after the end of the mission. When you do re-enter your object on ground, you have, on the other hand, to respect and prove that you don't have a risk higher than 1/10,000 of creating casualty on ground. This is done by calculation before launch. You need to prove it. Sometimes this is not obvious to burn, to demise the object while crossing the atmosphere, and recently there is a new science or a new engineering branch which is trying to design the satellites so that they demise, so they burn themselves when they come back through the atmosphere. If you move to the next one. So the issue is very simple. If you are not able to meet the requirement of 10 to the -4 of a casualty on ground, you have to do what is called controlled reentry. Basically, you will need to force your satellite to fall into the ocean so that you don't create casualties. Now, controlled reentry requires a propellant and requires specific subsystems. So if you can design your satellite to avoid controlled reentry, your satellite will be simple, much simpler. You will have a reduction in mass because you don't need to carry the propellant to do the controlled reentry. And when you talk about reduction in mass, you immediately talk about reduction in cost, simply because the more massive your satellites are, the more costly, but not only that. A satellite which are bigger costs more to be launched, and the launch cost is still a higher part of the mission cost. So the design for Demise is welcome in order to reduce cost and simplify the design. Next slide. I think it's the end for me, and I give over the word to Antonio. Antonio, you're muted. Jessica, you have to unmute Antonio. You can talk now, Antonio.
Perfect. Thank you, Jessica.
Okay.
Thank you. So, I will give an overview of the concepts of design for Demise. The first question is, how do we actually calculate the casualty risk of our spacecraft on ground? What we do today is, for fragments that have an impact kinetic energy lower than 15 joules, we consider these fragments not dangerous. Therefore, the casualty risk associated will be zero. Why? For fragments that have an impact kinetic energy above 15 joules, we will consider them dangerous, and we will calculate the casualty risk following the equation you can see in the slide. As you can see, this equation, this casualty risk, is actually a function of different parameters. Here you see the impact probability, then the population density, that mainly depends on the population distribution of the Earth's surface, as you can see on the image on the bottom right. And then we have the casualty area, the total casualty area of our spacecraft, or cross-section. As you can see in the image on the bottom left, the casualty area of each surviving dangerous fragment takes into account the projected area of the debris of the surviving fragment that impacts on ground, and the average projected area of a human body, which is equal to 0.36 square meters. Today, the compliance with on-ground casualty risk is assessed by simulation in re-entry analysis tools. And this is something that we can see in this slide. The problem with simulation is we have many uncertainties that affect this analysis, that affect the models we use in the tools, and there is the need to improve the knowledge about demise phenomena, about prediction, about demise events during the reentry, in order to develop validated and commonly accepted models. So, in order to do so, together with the simulation, we have identified other two areas in which we can improve the understanding of the demise: ground testing and flight experimentation on the right. In particular, more and more ground testing are being performed, mainly in what we call plasma maintenance facility and static facility. I will talk about that more in detail later. Ground testing in order to verify what we see inside the simulation. It's clear that there is also the need of flight experimentation in order to validate what we see in ground test and what we predict in our simulation. In general, these three areas address different aspects of the demise, so give us the possibility to improve the knowledge about demise in different aspects, but unfortunately there are some limitations related to each of these areas. I will go in details about that in the next few slides. This is about the simulation. So, as I already said, the reentry tools are used for on-ground risk assessment and include inside different models to predict the reentry. We have a model for flight dynamics, for aerothermodynamics, to simulate the heat transfer during the reentry, to simulate the mechanical stress, to try to simulate the fragmentation, and models for casualty risk assessment. What you can see in the middle is actually a video showing the simulation at system level. What we saw is a spacecraft tumbling slow at the beginning of the reentry, then faster. Then, due to the mechanical stress and the heat loads on the spacecraft, we have the breakup of the solar panel first, then the breakup of the external structure after, and the release of all the parts of the spacecraft and the equipment. During these fragmentations, different parts are released, are fragmented, and the surviving fragments will determine the casualty program of our spacecraft. As I already told before, there are unfortunately many uncertainties inside this simulation in terms of representativeness of the real reentry, in terms of accuracy of the models. For instance, the fragmentation phenomena today is not fully understood. It's based on reentry observation, and in general, it's let's say manually triggered during the simulation. At an altitude of 78 kilometers that we have seen in the past was the altitude at which there was the breakup. And at the same time, also the behavior of some materials is not fully modeled today. I can say that simulations today are able to assess reentry trajectory, within flux, casualty risk, but as I said, there are many uncertainties in the model simulation. About ground testing, this is something, I'm sorry for that. This is something we can see in this slide. To improve the understanding of the demise phenomena and to improve the full prediction, especially, let's say, to verify what we see in the simulation, today there are two main facilities that are used for tests on spacecraft equipment: static facility and plasma maintenance facility. In particular, in the static facility, they are used mainly to perform thermomechanical tests, therefore to observe the phenomena driven by temperature and mechanical forces on the demise. They are used to simulate the trajectory temperature profile, to simulate low heat flux, low forces, and this type of conditions are particularly significant at early stage of the reentry, so at higher altitude, where the atmosphere is less dense. About what we see in the middle, this is actually a video from a test in the plasma wind tunnel on a sample of magnetosphere. What we are able to do in the plasma internal is to perform what we call aerothermal tests. In this case, we are able to observe phenomena driven by the reentry flow, during an actual reentry of the spacecraft. This type of facility are mainly used to simulate high flux, high dynamic pressure, with the possibility to reproduce part of the physics, so shock waves and so on, and part of the chemistry that we could observe during the reentry. These conditions are particularly significant at later stage of the reentry, so at lower altitude, where we have actually the release of all the equipment, and we aim at demise this equipment, this part during the reentry. And of course, at this stage of the reentry, the atmosphere will be more dense. However, also in this case, with grad testing, we have many uncertainties in terms of representativeness of the full reentry condition. Let's say some of the events that happen during the reentry are not fully simulated, not fully modeled in this type of facility. In addition, of course, we have some physical limits related to the facility itself, like the size of the objects we can test, the orientation of our objects inside the facility, the power availability of the facility itself. So also in this case, we cannot be fully represented. And last, we talk about the area of the flight experimentation. For sure, there is the need to have flight experiment in the end, in the future, in order to get more data and to improve the understanding of the demise phenomena by having an actual reentry. And in this way, validate on-ground tests and simulation. What we have here is an example of reentry capsule experiment in the future, in which we actually put an experiment inside our spacecraft, and we try to get data to observe, to measure the different let's say, events, the different conditions we see during the reentry. In the middle, there was a video about the reentry observation of the spacecraft in the atmosphere. And also in this case, it's clear how many, let's say, fragmentation events we can see during the reentry, and how all the parts of the spacecraft are released. And some of these parts can survive and determine the risk on ground. Also in this case, for this type of area of flight experimentation, there are some uncertainties, some limitations. One of them is for sure the fact that it's difficult to set up the experiment, considering it's difficult to consider how we will actually follow the observation of all fragmented objects, how we will actually get the data that we need, and how we will transmit this data, considering also the issue during the reentry related to the breakout of the communication. So this was mainly about the general concept. In this case, with this part, I will more give an overview of the techniques of design for Demise. So how we actually apply the design for Demise. What we have in this slide, it actually makes clear that design for Demise is today applied at two different levels. Considering the on-ground casualty risk requirement that we have today, the system shall be compliant with these requirements, so the risk associated shall be lower than a human score. For the way it's today, this requirement that is applied at system level flows down at equipment level, where today we don't have actually a clear requirement. In terms of design for Demise techniques, we have different techniques that are being studied at system and equipment level. At system level, the main role of the system is it has to ensure the breakup and the release of all the equipment at conditions that are favorable for the demise of the equipment. And at the equipment level, the role of the equipment is, of course, to ensure the demise of all the parts and the fragmentation. We can say that in general, design for Demise is an iterative approach between system and equipment level, and it's a multi-level, since we have the two different levels in which these techniques can be applied. So what are actually the techniques I'm talking about? Starting, let's say, from the left of the slide, we can categorize this type of techniques in 4 different groups. The first one is aiming at minimize the required heat. It's possible to minimize the required heat, for instance, by reducing the mass of the object, so by reducing the actual amount of heat that our object needs in order to melt, in order to demise, or by replacing the material. This also means by using other materials that are more easy demisable, that are more easy to melt, for instance, considering materials with lower melting temperature. Another category of techniques aim at maximize the available heat. In this case, we can consider something like playing with the ballistic coefficient. What we know about the ballistic coefficient is, in general, for higher ballistic coefficient, the type of range of our spacecraft will be steeper. This also means higher gradient of temperature during the reentry, but this also means less time spent in the atmosphere accumulating heat. So this is a technique that is under investigation and needs to be more, let's say, understood and investigated in the future. Or we can think about increasing the local flux of our object. In this case, it's a matter of trying to change or try to consider the shape of the object. What we know today is, in general, sharper objects have, let's say, higher local heat flux in the Egypt compared to blunt objects. Or other techniques are about adding energy, for instance, in the case of exothermic reaction inside the equipment, the part we want to demise. The third category, in the third column you can see the slide, it's about optimize the structure. In this case, the main goal is to increase the heat flux that goes inside our spacecraft. For instance, an example are the ESA breakup technologies in order to ease the fragmentation of our spacecraft by opening the external structure earlier during the reentry, so at higher altitude. And this is the case of demisable attached points, or also the case of demisable joints, what we call demisable joints for external structure. The fourth category is about the minimization of the casualty area. For instance, one of the techniques that are under investigation, it's about, it aims at keeping together the fragments that we see difficult to demise. Means for those parts that, in terms of materials, in terms of the characteristics of the object itself, we cannot actually make fully demisable, and we can think about containing them with this method that is actually called containment. Some of these techniques today are just at conceptual stage, so they are not fully investigated yet, like containment, and they will be investigated more in the future in order to improve, let's say, the overall techniques about design for demise and aiming at the overall demisability of our spacecraft. What we can see actually in the next slide is something I was talking about before. So all the equipment are released during the reentry, but what we have seen from past observation and from past simulation, we have actually identified what we consider the critical elements of our system. Critical in terms of high probability to survive during an uncontrolled phase. In this case, we have identified different equipment, particularly risky. We are talking about, for instance, propellant tank, reaction wheel, magnetorque. The main reason of this criticality is mainly related to the materials of this equipment are made and the late exposure of this equipment itself. For instance, for the propellant tank, one of the main problems is the material. Today they are mainly made in titanium. Titanium has a really high melting temperature, so it's really difficult to melt, to burn. Another example is the reaction wheel. In this case, we have a combination between material and late exposure of the part. For instance, the reaction wheel is made of housing that shields all the parts that are inside. Especially one of these, this part is called a ball bearing unit. It's inside the reaction wheel. It's shielded by different parts, the motors of the reaction wheel, the housing, and so on. And in addition, this part is also made of a material, stainless steel, that is not really easy to melt, let's say. So in this case, we have a combination between housing that shields and that generates the late exposure of the part inside, and the material of the part inside. And then we have other critical elements like the case of the manufacturer, where we have the housing in general made by separately, and then compact coil, then inside we have the core. So also in this case we have a really late exposure of the internal part, and the material used inside could be really difficult to realize because high melting point. Other examples are large mechanisms, batteries, and so on. So those are today the main critical elements identified, and the one we want to make realizable through the design for the Demise techniques I was talking about before. With this, I will get to welcome any question about the part we just explained before starting with the next part.
Okay, Antonio, we have one question from Francois, just saying, what is the typical breakup altitude, and what does the breakup altitude typically depend upon?
What we have seen in past observation is actually that the typical breakup altitude is around 78 kilometers. I guess Tiago also has some answers to complement what I'm saying. I've seen that you were about to talk, sorry, Tiago. I will let you complement. That's 78. Okay.
Can you try to mute Tiago? Which is Tiago sign Antonio and myself to be unmuted.
Hello, so can you hear me now?
Yes, we can.
Okay. Now I was going to say that, I mean, that's a very good question. I mean, of course, the way the demise of a satellite is a process, so you will have parts that will demise at different altitudes and parts that will break up at different altitudes. But in early observations that were done, especially in the US, it was observed that in the range of 80 kilometers, so 70, 80 kilometers, we see several breakup events, and actually this makes physical sense because that's around those altitudes that we start having higher mechanical loads as well during the re-entry coming from the aerodynamics. So actually in many tools there is this magic number of the 78 that Antonio referred to, at which we assume that most of the equipment breaks out and is exposed to the re-entry environment.
Thank you, Tiago. I have also another question that I think related to that one. So it's coming from David, and it says, to avoid that big parts of satellites can rise to the ground, it was studied the possibility to create a kind of controlled fragmentation explosion that can happen at a fixed altitude or very high temperature. In a way to create very little fragments, but easier to be burned up during the re-entry.
So this is one of the techniques Antonio mentioned, but one of the techniques is indeed to design equipment and systems in a way that they break up earlier and that the smaller parts are then exposed and will melt easily or more easily, or that they are so small that they're not a problem anymore. So yes, there are techniques assessed like this. One has to think that the equipment looks like it looks for a reason and uses the materials it uses for a reason. So it's not always easy to change. But actually in the next part of the presentation, I'll show some examples where this will be.
I have a question on the operators. Do satellite operators adhere to design for tomorrow's principles? And if not, how can we get them to? This is from Daniel. Maybe it's for Stein, I think.
Okay. Thanks, Daniel, for the question. So, first of all, many countries around the world, either as part of their launch procedure or as part of their space law, they have this requirement that the risk should be below this 10 to the -4. Now, how do they get there is seldom identified. Such a very large spacecraft, what you're going to do if you implement a controlled re-entry. And what we try to achieve with design for Demise is to give an additional tool to those operators to avoid implementing unhealthy propulsion system. So in a sense, the regulations are the same for many states around the world. We try to add a tool to cope with them.
And I think just to complement what we have been observing as well is that a major point is to reach a good TRL on the technology side so that the operators and the developers of systems, system integrators, actually take them on board. And this is something we'll also discuss.
Okay, I have also taken another question. It's concerning the re-entry experiment. So basically there are two questions. One is for the IODs, if there is something planned in the near future. And then combining this one with the one from Xavier of how this can be funded.
Okay.
So I think this for Lisa.
Yeah. Maybe I can take it over when you talk about money. Usually it comes to me. Yes, you know that the issue of IOD is that IOD is extremely complicated because you can never really model the exact event with a limited budget. So the question is always how much should I spend for the IOD and how much will I really test with the IOD. So we are studying some experiments to monitor the demisability and maybe also to verify some of the elements like the joint. In which programs there are in ESA two possible programs, and we are flexible enough to use both. One is the GSTP, and the other one is the Space Safety Program. So both programs would allow to carry out such an IOD.
I think the next question is quite a complicated one from Sai on the re-entry tools. So, Steiner, Tiago, you'll need to listen to this. So, from your experience, what is the relative contribution of mechanical fragmentation during re-entry? For example, in Scarab, which is high fidelity, they perform FEM analysis at critical locations, but in low fidelity tools like Drama, they do not have such possibility. Is it worthwhile to include mechanical fragmentation in these low fidelity re-entry models? And then maybe in your answer, just to build upon this, what is the relative contribution of fragmentation by mechanical stress and crack propagation and by phenomena such as melting? That's a big one.
I give you the hot potato.
Excellent. So let's go backwards. So the question on the relative contribution is the same as the answer to what's the breakup amplitude. I mean, there's no single fraction that I can give here which is going to be right in all cases. So I'll not bite in that potato. What is exceedingly true is that the more tests we do, the more we, for example, try to devise tests which actively break up a spacecraft, is that we see that there are properties of the material which do contribute to either a faster or a slower demise of these components. So in the past, most of the tools, methodologies were always focused on the fact that demise is driven by the thermal degradation, thermal ablation. But yeah, the more we look, we see indeed that there can be contributions from mechanical breakup. This is definitely one of these points which are under active research at the moment, and whether they will eventually end up then into either a verification tool or a design tool, that we still need to mature the technologies to give a good answer to that, but definitely of interest.
Okay. So yes, I think that the last question for this term is the one from Benedetta. So she's asking how you can verify that a tank is demisable. Tiago, you can answer to this.
Okay, actually I would, instead of answer, maybe that's exactly the next part of the presentation. So we can actually, it's a good introduction to the next step. I don't know if I already have control. Yes, I have control of my computer now. So yes, it's a very complex process, and I've been given the task to try to explain it in the most simple way possible, and I've tried, so I hope you can bear with me, and I hope you understand everything I'll say from now on. Just putting it step by step, why do we need verification guidelines? So verification for Demise, as you can imagine, Demise is such a complex process. When a system or an equipment is re-entering the atmosphere, it will be tumbling in every direction, it will be getting heat fluxes, shock waves, it will be integrated in the system in a certain way. So all of this is extremely complex. So how do we verify Demise? We have these requirements that tell us we have to comply with the casualty risk on ground below 10 to the -4. This requirement, as Antonio said, applies at system level. So it means each satellite has to comply with a risk or has to have a risk of casualty below this level. And this brings us already to the first problem, meaning how can we actually cross-check different simulations done on the system or different verifications done on the system? We need to have the models corresponding to each other in as much as possible, and we need to be able to compare two analyses done on the same system or on similar systems by eventually competitive proposals. Then from the system that needs to comply with 10 to the -4, as you can imagine, you will have to tell the equipment, I have to have designed my system like this. The equipment has to demise under these circumstances, which means that we also need to be able to slow down the requirements from system to equipment level. And this is also something that is a gap at the moment, or that was a gap, and for which we need to have rules or, let's say, a level playground to assess how equipment will demise. And finally, when we get to what Antonio showed of models and tests, each one of the different tests and models have different strengths and weaknesses, and in the end, it's by combining them that you can reach some sort of verification. And this also has to be explained, because it's not obvious that just by taking any tool and modeling as you want, you will have a verification of demise. Of course, you can then tune all the simulations to do whatever you want, or just by a test, say, through this test I show that it is demisable. We saw before that the tests themselves cannot simulate the full re-entry, they can only simulate, and this is not enough to demonstrate demisability. So, but this time, we see that we need guidelines on how to do the modeling and tests so that we can do the demise verification both at equipment and at system level. And it was with this in mind that we started in ESA working on the demise verification guidelines, what we call DIVE. It's a technical note, so it's not at the level of a standard or a handbook. It's a technical note where we have collected all the knowledge that we have been gaining in ESA. We have been working on design for demise now for since 2012, so for 8 years in many different activities at all levels. And this technical note really gathers a lot of the lessons learned we have got during this process. So the technical notes will address issues at system level, but also at equipment level and material level. So at equipment level, you can also imagine that the guidelines or the way we do verification may be different if your equipment is actually inside the structure, or if it is outside the structure, or if it is a structural element that is connecting two other pieces of equipment, for which what you wanted to do during the re-entry and the altitude you wanted to demise may be completely different. Also for materials, you can imagine that the effects that lead to the melting of a metal are totally different from what happens to composites, where you have different layers and different materials included, or to ceramics that will also behave in a very different way. So in this document, you will find a breakdown in all these aspects. It's quite extensive work, and here I'll try to give you just an idea of the structure and guide you through the process of thought that we built during this work. First of all, we'll go through the system level procedure, and then I'll go down to the equipment level, and we will discuss how at system level the requirements must be conceived or understood, and then how these requirements will imply that the system modeling and simulations, to the critical elements assessment, and when it flows down, let's say, to equipment level verification. So starting with the requirements, as I said, and you've heard this number a lot of times, the requirement says that we cannot exceed 10 to the -4. This implies that all the equipment must demise with the reentry conditions enough to meet the 10 to the -4, but also that the system has to be designed so that it will expose the equipment to this heat flux, to the needed heat flux. So it has to expose the equipment when the equipment needs to be exposed, and so that it will either demise, or if it cannot demise, can it be also part of your risk budget. And this is exactly the first step that is also documented in DIVE, that at system level you should build what we call a casualty risk budget. Because within this 10 to the -4, there are parts that may not demise, but they have to be below this threshold. So when you build your casualty risk budget, you will see which parts are contributing the most. And another thing that we need to build at system level is to have knowledge, or to get to know at which conditions, release altitude and conditions, the equipment will be released. So when we start analyzing if the equipment demises, we should have this data coming from the system design. I cannot know how a tank will behave if I don't know with which initial conditions it is exposed to the external flow during the reentry. So this is a first step. And this is reached by doing simulations. DIVE has a very heavy number of rules on how to actually do this modeling. So it is important that the model is equivalent for different parts of the spacecraft, and especially if we identify critical parts for which we expect are driving the casualty risk, it is very important that they are properly modeled. Also, it is important to extract from the simulations that I just saw, so the trajectory that the system will see, and the release conditions of each of the equipment. As you can imagine, there are a lot of uncertainties in this process. I mean, there are uncertainties in the atmospheric parameters, on the trajectory that the spacecraft will follow, on the loads, we mentioned mechanical loads before, also thermal loads, on the materials behavior, on how the different parts fragment. This is very difficult to predict. And so what we have done in DIVE was also to quantify or propose methods to quantify the uncertainties so that we can follow a statistical approach to this calculation of the compliance with the 10 to the -4. Here, just to give you an example, we have put a graphic of some simulations on a structural panel to see what was the forces that it was experiencing. As you can see, this is above 85 kilometers altitude during the reentry, and you see that it changes significantly. So it's very hard to say a value for the mechanical load that the mechanical joint will be experiencing. So we need to have these uncertainties somehow quantified and addressed during the reentry simulation. Okay. Then, if we say that we have done this job, the verification of the compliance will then actually rely on these three steps. So how can I say that my system is compliant? I need to make sure that in my simulations I'm using verified critical equipment models. So all the equipment that is seen to contribute to the casualty risk, we have to be sure that the models are correct. We have to have a verified breakup sequence as much as possible, so we try to have to reduce the uncertainty at which altitude each equipment will be released. So we talked before about the breakup altitude. This, as I said, as I tried to explain, is a sequence, and we need to understand this as much as possible and make sure that we don't go above the 10 to the -4. And of course, all of this is to do with the uncertainties. So we have to be sure also that the proper uncertainties are taken into account. These three elements are essential to be able to say if a system is compliant, yes or no. I'll give you now an example just before going to the equipment level slides. about how our techniques that we call system-level techniques. When we talk about system-level design for Demise, it means that we ensure a certain breakup sequence. It doesn't mean that we break up everything as early as possible. As you will see, this is a preconception that is not always helping. It means that we want to know when and with how much heat and when each part will be released and experience the re-entry flux. So an example of a technology that we have been developing for this is the development of demisable structural joints. So the idea of these structural joints is that they actually break up earlier during the re-entry and that the panels can be released early. You see here in the video a test in a plasma panel that was done in one of these concepts. And with this development, we are moving, let's say, the breakup altitude of the first of the external structures from about 80 kilometers, as we said, around the 78 kilometers altitude, to above 90 kilometers. So that will allow the internal equipment to be exposed to the atmospheric flow much earlier. A very good example, because this is actually already being applied in a different case, not from the external structure, is on Sentinel-1 CD spacecraft. Actually here, it has been implemented also a demisable joint, here with the idea of separating the SAR antenna. A lot of fragments that were reaching the ground in the simulations were coming from the SAR antenna. And actually by changing the joint by a soldered joint with low melting temperatures, they allowed for an early separation of the SAR, and with this, the SAR fragments mostly demised, and they could be much closer to the 10 to the minus 4. Now we'll go to the equipment level procedure again, and we'll start by looking at how do we define a requirement at equipment level. And this is not simple, because as I said, this is in a way coming from the system requirements. Then we'll see how this impacts the modeling and simulations, the Demise tests, because tests cannot really be done. It's very hard to imagine that you can do a full test on an entire system, but you do it mostly at sub-assembly or equipment level. And then I will verify and correlate the models based on tests and simulations. So starting by the equipment level requirements, as we were talking about, you can have two different cases. You can have a case where you're doing or designing an equipment like a payload that is specific to a single mission, or you can also be designing an equipment that will be used in many missions, a generic technology, say a demisable tank or a demisable reaction wheel. In any case, if it is for a specific mission or a generic technology, what this means is that this equipment will have certain release conditions. In a specific mission, you can get them from the simulation of this specific system. In a generic technology, you must have a generic guideline that covers a range of missions. When we say release conditions, we are talking basically about trajectory conditions, at which speed it is going, in which angle during the re-entry, tumbling attitude, then at which altitude it is released, and with which temperature it is released. So actually it's based on these three elements that we built a requirement or a formulation of a requirement for equipment level. So the equipment shall demise when it's released at a certain altitude or above. So we say if it's above that, it should also be demisable. Within a certain re-entry corridor that can come from a specific system design or from a more generic assumption, and assuming an initial release temperature. I'll give you an example. So when we talk about propellant tanks, that is something that is internal to the spacecraft, normally what we have assumed was this typical number of the 78 kilometers. We said if it is released at 78 or above, it should be demisable, because we believe this is a credible number from observation that the system can also reach. Then we say it has to be demisable in a range of LEO initial orbit. So you are in a LEO circular orbit, you re-enter uncontrolled. We have in Dive's document actually defined the corridor of parameters of trajectory that will allow you to say, yes, for most of the LEO spacecraft, I will be compliant. And then the release temperature, as it is an internal equipment and we don't have a specific design of the system to know at which temperature it will be, we assumed room temperature, so 300 Kelvin. This is just 3 values, but for each equipment, you can define these values accordingly. So if it is an external equipment, for example, you may have a higher release temperature because you know it has been heating up during the first phase of the reentry. Then we go to the next step. We have the requirements. We need to do a simulation, which means we have to build a model. And how do we know if our model is right? One of the first questions to ask is, are all the parts that are relevant models? I mean, parts that have enough mass and are in a material that is hard to demise. Are they all models? The story of the 15 joule when they reach the ground. And the second point is, do we know the material properties of all these parts? And if you don't know, you may need to do a material level verification. That is a test at material level, like coupon level, to understand if the material demise properties are as you expect or if they are very different. Then another question is, am I considering all the uncertainties? Am I considering that it may break up a few kilometers higher or lower? And last question, is the simulation representative of the demise events? Imagine you are trying to represent a certain fragmentation like we have here in the reaction rule. In the reaction rule simulation that you can see here, we have to observe a number of events like the housing melt, the flywheel separation that you just saw here in the video, and then even later you will have the ball bearing unit separating in different parts. Are all of these representative? For example, are the combinations between the thermal loads and mechanical loads taken into account? It's very hard to do this today in a simulation. So the way to get around it is to validate or anchor, let's say, the simulations into demise tests. And that is the next step. So how do we go from the simulation to defining demise tests? So we start from the simulations, and as I said, you identify the main events that happen during the demise. I melt the housing, I separate the flywheel, and these events happen, one can estimate which are the driving parameters that are driving these events. So for example, if they are driven by temperature, then maybe you can do a test just in a furnace or in a static heat chamber. But if they are driven by flow effects or chemistry, or if we don't know exactly if these aspects have an impact, maybe you need to go to a more complex test in a plasma internal. So based on the driving parameters, you will be able to define what are the test conditions that you need, and with this, the facility that you will choose, and finally the test definition. So this is a process that is quite iterative, and actually what we have been observing is that every test we do normally turns out to be a surprise. I'll give you here an example of magnet torque tests that we have done. Actually, what happened is the first phase, the housing that we expect to melt, or in our model melt, spilled out. Then you see a regression of the potting material, that is the resin, and then slowly you see the coil starts melting, but it doesn't go all at once, it goes layer by layer. And finally, it starts exposing the core material. Here is a ferromagnetic material that, for which the emissivity was not properly modeled. We didn't know how much was the emissivity when we get to such high temperatures. And also there was a very interesting effect that when it started melting, the emissivity changed completely. So actually all of this we could not foresee at first from the models. And with this in mind, we go to the next step. That is, how do we bring them from the test conditions to a correlated or validated model? This is an iterative process. And as you saw when we do a ground test, I hope you see my mouse, you are actually putting the equipment in a condition, a predefined condition, that's for which you have simulated and you expect certain event to happen. You do the test, you see if the event happens in the conditions that you expect. So the event A has been tested, and then you see that probably it happened in a different way than you expect, or not, but if it did, then you have to modify the model so that it mimics this event. And you do this sequentially to all the events that have been identified for your equipment. Once you have a simulation model that has been that is linked to the test and has been properly mimicking everything that happened in the test, under the test conditions, then you are much more certain than when you do a full simulation re-entry that will go through all the phases, will be tumbling, etc. You can extrapolate this model, and you can actually get a verification of its demise that is more realistic than what you knew from the first model. I'll give you an example of what I just told you before. So this is the type of results you get from a plasma internal. This is quite complex, but what I want to show you here is that we saw in the first condition at which heat flux accumulated before the TFRP housing was actually removed. Then you saw how long it took, and under which conditions the potting started to burn back. Once the potting disappeared, we saw that the copper layers start melting one by one, as you can see here. And finally, we see how the core starts heating up and when it finally melts. So each of these are different events, and in the end, you make your simulation model meet these events at the right conditions before you bring it back again to a proper re-entry condition. So this is how you correlate tests with modeling. And as you see, the difficulty has been growing. So this is the most difficult part I have to show you today, actually. And then I wanted to give everybody an idea of what is the thought process for a design for demise at equipment level. And we do it for a reaction wheel example. Here we can see that the requirement was that the reaction wheel should demise completely when released at 78 kilometers or above. And this meant that we started by looking at how a normal reaction wheel, that in this case had a flywheel in stainless steel, would behave. And this is the blue line that you see in this graphic. So in this graphic, you have casualty area in the vertical axis, and you have the release altitude of the equipment in the x-axis, in the horizontal axis. And you see that for the blue line, even at 96, some of the simulations showed casualty area. So some fragments were surviving, even if you would release the equipment at 96 kilometers. This probably means that even if the reaction wheel was directly released in flight, it will have a chance that some parts survive and contribute to the casualty risk of the whole spacecraft. And then it starts growing. So here in all simulations, you are seeing one fragment, in this case, surviving. And actually, as you go down, you see that at a certain altitude, you start having more small fragments that did not demise. Here you have two fragments, that is the flywheel and the ball bearing unit. And then you have basically the full reaction wheel intact. If it's released too low, say at 60 kilometers, nothing will demise and you have the full reaction wheel. So one of the first things that this tells you is that, yeah, we think higher is always better, but it's not the case. I mean, if you start releasing higher, it may be that some of the fragmentation events will not lead to a demise of all the fragments. So it doesn't mean that all the releases, the higher releases, are better than the lower ones. What we did to make it more demisable, the first step was to change the flywheel material by an aluminum flywheel. When we did that, we see the red line here. So at 96 already we had a full demise. But at 87, there is some cases that did not demise fully, but there are some cases that did not demise fully. And then it starts growing to at 78. All the time we have part of the reaction wheel, one fragment, one big fragment surviving. So actually for this option, this first design for demise option, we could go from no demise to a demise altitude of 96 kilometers. But this was not enough to meet the 78. So we went to a second step that was let's try to disintegrate the ball bearing unit, because the unit you see here at 87 surviving and 78 is the ball bearing unit. So if we separate the motor, then the motor is not shielding this unit anymore, and we expected to see more demise. That was true. So what you see here in blue was the red one of the previous slide. And here in blue you see that at 87 you still have some fragments, and now that we separate the motor from the BBU, in the red line you don't have any fragments left. So actually, by doing this disintegration, this early disintegration, we have a full demise altitude that went from 96 to 87 kilometers. But once again, we are not yet meeting the 78. So we have to go to a third step. That was to change another part of the ball bearing unit. So again, at 78, the part that is surviving is the ball bearing unit. And we needed to change the oil chamber material because by demising this oil chamber material, we will not be shielding other parts of the ball bearing unit that are inside it. And by doing this, we see here in the curve that then the red curve now, that corresponds to the new option, is demising completely at 78. So we were able to meet the requirement of 78 according to simulations. We still have to verify it, going through all the dive process that I told you before. But this tells you something. This tells you that design for demise, it's a complex process, of course, but first of all, we need to avoid preconceived ideas that just by releasing higher or by breaking up earlier, we have a lower casualty risk. This is not true. It really depends on a case-by-case basis. And it is also a highly iterative process. Actually, I show you here 3 steps, but I think we did more than 30 options before we reached this combination. And actually, it's only, in most of the cases, through a combination of different techniques and disciplines that we can comply to design for demise requirements. I didn't lose you there. I'm going to finish very soon. I just want to say that, in ESA we are working on design for demise at many different equipments for reaction wheels, magnet torches, electronic boxes, tanks, optical payloads, materials. And this is a very complex work, but that dive, I think, will make much more consistent. And for dive, I wanted to say, as I told before, this is a living document, it's a technical mode. So actually, we did this webinar also with the intention of sharing this knowledge, but also to get feedback and comments. So, especially for ESA member states, industry stakeholders, you can contact us if you are interested in getting the dive report. And if you have feedback for us, please contact us. We will be very happy to evolve this document and to apply it. There's also another very important tool for us and for the community that is also available to all stakeholders in member states. That is the estimate database. This is a database where we store all the test data. So you will find there tests at material level, also facility description, and you can go to this link and create a user for you. Also, equipment level tests that we are doing for all the equipment mentioned before will be available there. And finally, I want to get almost to the conclusion, but to say that our vision for the design for demise has been set starting in 2012 with system studies. Then we started to understand what were the critical parts. We started studying each of these parts. We started to test at material level, and that's all the knowledge that allowed us to build dives, to build these documents. And the next step for us is really to verify and to qualify technology for flight. So we expect to have the design for demise technologies verified already in the upcoming Copernicus missions for Earth observation in ESA. And we're also working indeed in trying to find opportunities for flight experiments. So this at spacecraft level, at launcher level, this is a very important step for us also, so that all these assembly simulation runs, tests, and flight experiment can really consolidate the verification process in the knowledge. So just to summarize this whole presentation, there is indeed an urgent need to meet this 10⁻⁴. There's a big system impact and cost impact of trying to do controlled reentry for every mission. Design for demise is this intentional design of systems and hardware so that they disintegrate during the atmospheric reentry. And the future platforms would really benefit from having these technologies, these design for demise technologies available so that they can do an uncontrolled reentry. In ESA, we have many activities ongoing, many developments at both levels, system, equipment, materials. And we have then compiled these design verification guidelines that are now available to the European and the ESA member state stakeholders. I would just, before going into the questions, like to say I thank you very much for following us during this second webinar. There will be a third one on the 24th of June. And this one, the next one will be dedicated to eco-design. That is another very important area of CleanSpace. that is to deal with the environmental impact of space assets on ground. And I think we can go to the questions. I will just tell you to follow us also in our blog and contact us if you need, including in our through the email. And if you want to help us out making these webinars even better in the future, you can use this QR code or the link in the slides to fill a survey and give us your feedback. So I'll be happy now to try to answer some questions with my colleagues. Thank you very much.
Diego, there is many questions, so we will try to wrap up a little bit what has been asked. Maybe the first question I will ask it to Antonio. There were many questions about the facilities that are in Europe to do this kind of tests. So I don't know if you can answer to that one.
Yes. Thank you, Sarah. Can you hear me?
Yes.
Perfect. So, yes, I saw the question about the facility. Actually, was from Omali. There was an answer given by Stein, and I actually complemented it. Basically, the test facility today try to mimic what happens during the reentry, but they cannot really mimic the full reentry conditions. What can be done inside the facility, for instance, inside the plasma with Daniel said, we can try to replicate the total amount of entropy of energy that an object seen during the reentry, but we cannot replicate the real dynamic of the object. At the same time, in a static facility, we can replicate some temperature profile during the trajectory, some low heat flux, but also in this case, we cannot replicate the flow condition, the real flow condition. So the real answer is inside the facility at the current status of the technologies, we can replicate some phenomena during the reentry. We can try to simulate, but we are not able to mimic the whole trajectory and the whole conditions during the variation of the altitude during the reentry.
Thanks, Antonio. Next we have this question was asked twice, maybe it's for Tiago. And could we use spiral actuators to open up the spacecraft structure in order to enhance demisability?
So we have looked at many options. We try, the actuators in the sense that they're actuated by the system is not truly the preferred option, because we prefer options that even if the spacecraft is completely non-operational, can still break up the joints and separate the panels or the equipment that we want to separate. But yes, spiral materials, pyrotechnic materials or exothermic materials, as Antonio referred, have been looked at to be used also in a passive way. Not only by us, but also by other colleagues in Europe like me.
Thank you, Diego. There is also another question about which parts of the spacecraft are suitable or not suitable for design for Demise.
So it's not about being suitable, but it's the way. Yes, there is a combination in a way of things that are critical, because otherwise you don't need so much design with all the design changes that are needed for those parts to be nice. So, for example, our strategy at the moment has been to focus first on platform equipment, because it will be used in many different missions. So it's, if you do those developments, they will be having an impact on several missions. And also because, for example, optics are very difficult to change. Those materials are very stable to thermal changes because of their optical performance, and so it's much harder, and it's one design that normally is already very stretched, let's say very constrained, and it's hard to change to make more demisable. So our goal is indeed to have techniques that can really increase a lot the range of missions that are demisable and that can do an uncontrolled re-entry. But Within that type of equipment that are more suitable, as Sarah said, I think we can include tanks, we can include magnet torquers, we can start to include reaction wheels that in the beginning nobody thought could be demisable, but also others like other mechanisms, carbon, and others.
Thanks, Tiago. I think we have just a practical question at the moment, maybe to Jessica. Jessica, what's the plan for the recording of the webinar? How will we distribute it to everybody?
Actually, we will just distribute to people who are going to ask for it. It's quite a heavy file. So if you need it, if you want it, you just email us when we email the PowerPoint presentation. Was it clear? Yes, and I think we need to complement the question on is the recording of the first webinar available, and the reply is not. In a very simple way, because it was the first time we were using the tool and we could not record it in a proper way. So we are slowly, I guess, like everybody in this situation, becoming more familiar with these tools.
Thank you. Lisa, maybe there is another question for you, or I don't know if Tiago wants to answer. It's about the distribution of dice.
Mm-hmm. So at the moment it will be done by email. So if you are interested in this document, please contact us and we will come back to you. And we expect that in the future it could also be linked to the estimate database login so that it will be available there.
So, yes, maybe we can ask the last question is when or where is the time for Demise going to make the difference?
It's true that we cannot expect that every satellite will demise or comply with the 10 to the minus 4. When we talk about satellites of many or several tons of mass, it's hard to imagine that even with all our efforts you can make it demisable. So actually today we see that satellites with masses as low as 500 kilograms can already be close to the threshold of 10 to the minus 4 when they have optical payloads, for example. And so our goal is to increase these thresholds to higher masses. I think we can, depends on the payload of satellites, but up to around 2 tons. But again, this is really system dependent, and we cannot say it for all of them. But I think it is useful for spacecraft in this range between 500 kilograms and 2 tons.
Okay, I think it's 4:15, and I would suggest that we close the webinar because otherwise, I guess some of these people could be talking about it for forever, and you will not have dinner night or whatever else. So thanks a lot to everybody, and I hope you enjoyed this overview of what is being done and now how we are planning to verify the demisability. Thanks for joining this CleanSpace webinar. Let me remind you that at the moment we have foreseen another webinar basically in 1 month on the 24th of June at 3 o'clock on eco-design, in which we will tell you what are the activities that we are doing in ESA to evaluate the environmental impact of space activities, and also how to introduce eco-design into the space design, and also presenting a database that can be used to evaluate environmental impact. So for the one interested, please join us for the next webinar, and we will advertise it through the typical channel that we use, the Twitter, the LinkedIn, our blog, and I would also suggest that if you have some specific topics, well, not too specific, but if there are topics which are of your interest you would like us to organize a webinar, please do not hesitate to suggest. We have used this tool of webinars to replace the so-called CleanSpace Industrial Days, which because of the present health situation could not take place. We moved the CleanSpace Industrial Days to September, but then we had to cancel it again, so we know we don't have them in 2020, and we will be happy to provide more webinars in September and until the end of the year. So thanks a lot to everybody, and see you next time.
Thank you.
Thank you so much, everyone. Bye.